Welcome. In today's video, we are diving into a groundbreaking scientific discovery, the detection of equatorial plasma bubbles, EPBs, over the Great Pyramid of Giza in Egypt. Now, what makes this discovery so remarkable? It's not just that these plasma bubbles were detected, but how it was done, from the Earth, using a Chinese ionospheric radar located over 8,000 kilometers away on Hainan Island in the South China Sea. This unprecedented achievement marks a major leap forward in our ability to monitor the ionosphere, the layer of Earth's atmosphere where these plasma bubbles form. But what exactly are plasma bubbles? EPBs are regions of differing plasma density in the ionosphere. When a dense layer of plasma overlaps with a less dense one, these hollow structures emerge, and they can grow to hundreds of kilometers in size. These bubbles are particularly common at low latitudes and are influenced by solar activity. And why is this important? Because plasma bubbles can disrupt GPS signals and satellite communications. Knowing where and when they form could help prevent outages in global systems, making this discovery crucial for technology-dependent societies. If you're finding this content fascinating, don't forget to hit that like button, subscribe, and ring the notification bell so you won't miss any future updates. And if you'd like to support our work, consider donating via the QR code on your screen or the link in the description. Now that we've touched on what plasma bubbles are, let's explore the technology that made this incredible detection possible. The breakthrough came thanks to LARID, the long-range ionospheric radar in low latitude, designed by Chinese scientists. LARID isn't just any ordinary radar, it overcomes some of the most significant challenges that have historically hindered ionospheric research. Most radars face a common problem, the curvature of the Earth. Conventional radars can effectively monitor what's above them, but as they attempt to observe farther distances, the horizon gets in the way. Essentially, anything below the horizon becomes invisible to these systems. This limitation has long been a roadblock in long-range monitoring of ionospheric phenomena. What sets LARID apart is its ability to bypass this constraint by emitting high-powered electromagnetic waves that reflect back and forth between the ionosphere and the Earth's surface. This reflection process allows the radar to skip across the planet, giving it an extended reach that goes far beyond the capabilities of traditional systems. In fact, LARID can observe phenomena occurring thousands of kilometers away from its actual location. In the case of this groundbreaking discovery, LARID, positioned on Hainan Island in the South China Sea, was able to detect plasma bubbles forming over the pyramids of Giza, nearly 9,600 kilometers away. But LARID's capabilities didn't stop there. It simultaneously tracked other regions, covering an immense geographical range that extended from Hawaii in the east to Libya in the west. The ability to monitor such vast and distant areas in real time was a first in the world of ionospheric science. The construction of LARID in 2022 marked China's entrance into an elite group of nations leading the charge in atmospheric research. However, LARID's real triumph is its unprecedented ability to track equatorial plasma bubbles, EPBs, in real time, directly from the Earth's surface, without the need for space-based instruments. This technology has opened up possibilities for building a global network of radars, which could monitor and predict plasma bubble activity worldwide, a critical step in mitigating the disruptions caused by these phenomena. Furthermore, by understanding the behavior of these bubbles, scientists can work on improving satellite communications, GPS accuracy, and overall reliability of global communications systems. LARID's innovative approach not only enhances our understanding of the ionosphere but also paves the way for a future where space weather forecasting becomes as integral as meteorological forecasting is today. A pivotal aspect of the recent discovery involving plasma bubbles was the geomagnetic storm that occurred between November 4th and 6th, 2023. This storm was key in triggering the formation of the equatorial plasma bubbles, EPBs, that LARID was able to detect in real time. But what exactly is a geomagnetic storm, and why is it so important in this context? Geomagnetic storms happen when the sun releases large bursts of solar wind and magnetic fields that collide with the Earth's magnetic field. These interactions are particularly intense in regions near the Earth's equator, where the plasma density in the ionosphere is naturally higher. When the solar wind, filled with highly energetic particles, strikes the Earth's magnetosphere, it causes a sudden increase in plasma activity. This surge in activity can distort the ionosphere and create these plasma bubbles, which are then carried along by the Earth's magnetic field. The storm of November 2023 was particularly notable because it occurred during a period of heightened solar activity, and LARID's detection coincided perfectly with the arrival of solar particles into the Earth's atmosphere. As the storm unfolded, LARID tracked the plasma bubbles forming over several regions, including the Pyramids of Giza. This real-time observation of plasma bubbles moving and evolving was a first in scientific history, marking a significant leap in understanding how these structures behave during geomagnetic disturbances. What makes geomagnetic storms like this one so impactful is their ability to generate disruptions in communications and satellite systems, which are vital to modern-day life. The electromagnetic disturbances caused by plasma bubbles can interfere with GPS signals, satellite communications, and even military radar systems. In severe cases, geomagnetic storms have been known to cause power grid failures and interrupt air travel, which is why real-time tracking and forecasting of plasma bubbles is so crucial. LARID's ability to observe these plasma bubbles as they formed and moved during the storm provides scientists with a better understanding of how these structures develop and spread. In the past, such observations were only possible through space-based satellites or in situ measurements, which were limited in scope. With LARID, scientists can now monitor these phenomena from the ground, giving them a clearer and more comprehensive picture of how plasma bubbles behave over time. This storm also underscored the importance of being able to predict when and where plasma bubbles are likely to form. By tracking solar activity and understanding how geomagnetic storms affect the ionosphere, scientists hope to improve our ability to forecast these events. This kind of knowledge could be key to preventing large-scale disruptions in satellite-based communication networks, GPS systems, and other vital technologies that rely on a stable ionosphere. The geomagnetic storm of November 2023 served as a real-world test for LARID's capabilities, and the results were extraordinary. The radar's ability to track plasma bubbles in real time during such a significant solar event not only demonstrated its effectiveness but also opened up new possibilities for future research and technological advancements in space weather forecasting. The detection of equatorial plasma bubbles, EPBs, isn't just an exciting scientific milestone, it carries real-world importance that affects both everyday life and crucial global systems. These plasma bubbles, though largely invisible to the naked eye, can have dramatic consequences for modern technology, especially in an age where global communication systems, satellite navigation, and even military operations depend heavily on stable ionospheric conditions. So, why does detecting EPBs matter so much? To understand this, we need to look at the role of the ionosphere, the layer of the Earth's atmosphere that contains charged particles. This region is crucial for the transmission of radio waves, satellite signals, and GPS communication. When EPBs form, they create large pockets of irregularities in plasma density. These pockets can distort and scatter the radio signals passing through them, resulting in disruptions to the systems that rely on these transmissions. For example, GPS signals can become inaccurate, which can be problematic for everything from smartphone navigation to the precise timing systems that support financial transactions and military operations. EPBs are also known to affect satellite communications, which are critical for weather forecasting, broadcasting, and national defense. Even slight interference in these communications can have far-reaching implications, particularly in sectors that depend on consistent and precise data. In extreme cases, large-scale EPBs have the potential to cause disruptions to air traffic control systems, naval operations, and even global financial markets. The ability to detect and track EPBs in real time, as demonstrated by LARID, is a monumental step toward mitigating these risks. Before this technology, scientists primarily relied on satellites to study the ionosphere, and while effective, satellite observations were often limited in both range and real-time capabilities. LARID's ability to monitor EPBs from Earth over vast distances opens up new opportunities for building global monitoring systems. Imagine a future where plasma bubbles could be predicted and tracked much like we forecast weather patterns today. Such a system would allow governments, industries, and everyday users to prepare for periods of geomagnetic turbulence, minimizing the impact of EPB-induced disruptions. For instance, airlines could adjust flight paths to avoid areas with significant ionospheric disturbances, while communication companies could reroute signals to prevent service outages. Another critical point to consider is how EPBs are influenced by the sun's activity. Solar cycles play a significant role in the frequency and intensity of plasma bubbles, meaning that as we enter periods of heightened solar activity, the likelihood of EPB-related disruptions increases. Understanding these solar patterns and their impact on the ionosphere will be crucial for anticipating future space weather events. Additionally, research into plasma bubbles isn't just about preventing technological disruptions, it's also about expanding our understanding of the Earth's upper atmosphere and its interaction with space weather. The insights gained from tracking EPBs could help improve our knowledge of the complex processes that govern the Earth's magnetosphere, ionosphere, and their relationship with solar activity. In short, detecting EPBs is not only crucial for safeguarding modern technology, but it also represents a leap forward in our understanding of space weather and atmospheric science. The work being done with LARID and similar technologies is paving the way for a future where plasma bubbles can be monitored and predicted with the same precision as other natural phenomena. This will be vital in ensuring that the technologies we depend on remain reliable, even in the face of the sun's unpredictable activity. The importance of real-time EPB detection cannot be overstated, as it will play an essential role in reducing the vulnerability of global infrastructure to space weather. By tracking these plasma bubbles, we gain a better understanding of their behavior, allowing us to take preemptive measures to safeguard crucial technological systems. Looking ahead, the development of LARID marks the beginning of a new era in space weather monitoring. The potential to build a global network of long-range ionospheric radars could revolutionize our ability to predict and track plasma bubbles, EPBs, in real time, providing crucial insights into how they affect our technology and daily lives. By enhancing our understanding of space weather, we can protect global communications, GPS systems, and more. If you're fascinated by the impact of space weather on our world, subscribe to stay updated on groundbreaking discoveries like this. Help us continue exploring the mysteries of the universe by donating via the link in the description.